So after a short break, we will start the section 3, volumes by cylindrical shells. In the last section, we discussed the disk and the washer method. Okay, those two we summarized. We called the disk and washer method, which means the cross section gives a circle or the cross section shape gives a ring. But those two methods will be limited. Now let's check this example. Okay, this example. Find the volume of the solid rotating obtained by rotating this region. So here the function is 2x squared minus x cubed. And this region is under one function curve, just under one function curve from 0 to 2. And then rotate this region about y-axis. Okay, rotate this region about the y-axis. Let's think about this problem. Okay, I think it should be easier to write to show the solid. Okay, to show the solid. I just did a little zoom out. Okay, zoom out. Sorry. From 0 to 2. And then if we rotate about y-axis, then you will get this solid from minus 2 looking like this one. Okay, looking like this one. They are symmetric actually. Oh, let me just show my x-axis. From minus 2 to 2, right? So that will be how the solid looks like. Right? And then this time, it will be much easier to cut from y, right? It will be much easier to cut the solid from the y. And let me show you a different color. So you can cut for y, you can cut at some point y, and then you can get a solid. It looks like the cross-section solid gives a ring, right? Gives a ring. The inside part will be empty, and this part is shaded. If you're looking at this cross-section shape from the positive y-axis, that will give a ring. Okay, that will give a ring. So if we try the washer method before, that will be the cross section will be pi outer radius square minus pi inner radius square. But this one will be much difficult to find the inner radius as well as the outer radius. Okay, why? Why the inner radius and outer radius will be difficult? Because if you here we use y, so you need to express the function using x and using x. So you should solve this function, express the x using y. And to figure out the inner radius and the outer radius, we need this one we call the xl. Okay, what is the function for xl? What is the function for xr? And this part we can record the region between two curves, the area between two curves, if we are going to use the y as a variable. So let's check the examples. Okay, let's check the examples. For example, if we have the region between two curves. So this one we call the left curve is XL. The right function curve is XR. Of course, they are different function curve. And then from 0 to D, right? From 0 to D. So here, of course, the XL and XR, they are different. They are different function curve, okay? They are different function curve. XL and XR are different. But here, in this region, just one function curve, and it's a cubic function. Of course, we are going to have more than one expression for the x. Okay, so you can solve the x using y to get XL and XR, but it will be more complicated to rewrite the x using with the cubic function of x. It will be much difficult to solve the x when we have the term x cubed, right? So looks like the washer method could not work in the easy way for this problem to find the volume of the solid if we're rotating about the y-axis. Why? Because the inner and outer radius are not easy to find. Okay, the inner and outer radius of the washer are not easy to solve. Then to solve this kind of problem, okay, to solve this kind of problem, we are going to give a more general description of the problem, and then we will solve this specific one later. So what is this kind of solid? What is the volume of this kind of solid? So first, this is the region formed under one curve, right? Under one function curve. This is the region under one function curve from A to B. Then we rotate this region about either, let's say, x and y axis. That will be much easy. If it rotates about some other horizontal line or vertical line, that becomes more complicated, as the example 5 in the previous section, right? Now let's describe this problem in a more general way. So we will use the method called the cylindrical shell. Okay, we will call the method for cylindrical shell. Now let me describe those first. Okay, let me explain what are those shell. So here there are two cylinders, the inner side, okay, the inner cylinder and the outer cylinder, and we are interested in the volume of the shell between those two cylinders. So which means the inside of the smaller one, the inside part of the inner cylinder is empty. Okay, is empty. Let me give you those notations. Okay, uh, inner cylinder. Let me explain those notation first. We are going to formulate the volume expression for cylindrical shell. Then we will solve the previous uh, volume of the solid. So inner cylinder, and we need to work a long way. So be patient. Okay, be patient. Outer cylinder. Inner cylinder. So the radius, of course, here we have the inner radius for the radius for the inner cylinder, the base, right? The base circle we will use R1, and outer cylinder the base circle will be R2, and then the volume for the inner cylinder will be V1, and the volume for outer cylinder will be V2, and the height for both will be the same h, right? Will be the same h. Now, how can we find the volume of the shell? And the volume of the shell actually is the volume between the inner cylinder and the outer cylinder. So of course, the volume for the shell, I will use V. The volume for the cylindrical shell, we call the cylindrical shell. The volume for the cylindrical shell, V. Let me express this way. Okay, let me express this way. Of course, will be the outer cylinder's volume minus the inner cylinder's volume. Right? It's much easy, much easy. So outer cylinder's volume. So will be pi the base circle area times the height minus the volume for the small inner cylinder, right? It's pretty easy. It's pretty easy to express the volume of the cylindrical shell, which means this part, right? Which means this part. And we know that for the cylindrical shell, if you cut it, the cross section will give the ring. Of course, there is no problem, right? There is no problem to understand that. So this is the volume of the shell, what we are talking about. Now I'm going to rewrite, okay? I'm going to rewrite this volume. Pi R2 square minus R1 square times H. Here, the cylinder, no matter inner or outer one, they are fixed. So those radius will be fixed. So I will factorize this term as A squared minus B squared. So I can rewrite it as R2 plus R1 times R2 minus R1 times H. Okay, so with the algebra formula, okay, algebra formula. Now we know R1 is the radius of the inner circle, R2 is the radius of the outer circle. Then I will let the difference be delta R, which is R1 subtracted from R2, okay, which is the difference. So here denotes the delta R, okay, here denotes the delta R, which is the difference between the inner and outer radius. And then I will let R be the average of R1 plus R2. What does this R mean? This R actually is R1 plus half of the delta R. Okay, half of the delta R. So what is the circle? What is the circle with radius R? Let me show you in a different color with yellow. Okay, with yellow. So the circle, where is my pen? Where is my pen? Let me change it another color. So let me show you the circle with radius R. Okay, circle with the radius R. What is R? Average of the inner and outer radius. Circle with radius R in the purple color. Circle with the radius R. So you notice that is the R. How can we express the R? That will be R1, the inner radius, plus half of the delta R. So which will be the average circle between the smaller one and between the inner one and the outer one. So that is the circle with the radius R. So everyone is clear? So that is R, okay? That is R, which is the average of R1 and R2. And we use the purple color to denote a circle with the radius R. Then let's come back, okay? Let's come back for the volume of the cylindrical shell here. So I can write R1 plus R2 as pi times 2r, and then times delta r times h, right? So I can rewrite the volume V. I can write my volume V, the cylindrical shell, okay? The cylindrical shell, the shell between the outer and the inner cylinder. I can rewrite it, okay? So it would be 2 pi r times h times delta r. How can I understand this expression? What is 2 pi r? So if we know the radius is r, this r is also gives another circle in purple color. So 2 pi r actually is the circumference of the purple color I showed here, right? So actually the 2 pi r is the circumference, okay? Circumference. What is the h? Of course, the h gives the height of the cylinder, right? Of the cylinder or the cylindrical shell, it's the same height. What is delta r? Delta r is the difference between the outer and inner radius. I can call the delta r as thickness. Okay, I can call the delta r as thickness. So we can formulate the cylindrical shell's volume as this formula, as this expression. Circumference 2 pi r times the height of the shell times the delta r, thickness, okay, thickness. So that is more general expression or description for the cylindrical shell's volume. Okay, what does this V denote? That is the cylindrical shell. Okay, that is the volume for the cylindrical shell. Now, why we discuss this shell? Okay, why we discuss this shell? Now, let me repeat the problem again. Okay, repeat the very beginning, the example we pop up. So here under one function fx, okay, under one function fx, and how can we describe this region R? Let me describe this region R. This region R will consist about the point xy. Where is my x? So my x should be between A and B, right? My x should be between A and B. And where is my y? The y should be above the x-axis and below the fx. And of course here the function value we discussed should be positive, okay? So let S be the solid. This S denotes the solid. Obtained. Okay, how can we get this solid? We get this region first. Okay, we form this region. How can we call this region? This is the region under the function curve f between A and B, right? Between A and B. Under one function curve fx between A and B. So that is we call the region R. Okay, region R. And we can express in this way. And then for this region, we are going to rotate this region about y-axis. Then we obtain this solid. And we know the outer bound is this curve, okay? Is this curve y equals fx. So here, okay, here the inside cylinder is empty, okay? Let me show you the color, okay? In blue. So here, because there is some difference, there is some some empty part between 0 and A. So if you rotate this piece of region, the inside cylinder is empty, okay, is empty. So that is how the solid looks like. Try to imagine, okay, try to imagine this solid in 3 dimensions. So here gives the empty